Morning, folks. So, last time I started going over Lab 2, covered a variety of different things from the general numerical integration scheme to how to convert from floating point to fixed 16, 2.16. Any questions about this? I know that one group at least got the Modelsim stuff going with a full model, right? How was it converting MATLAB floats to 2.16? Did it work the way?
Round into something easy.
Oh, I said it's going to be a quarter.
Yeah.
All right, so you can do it by hand that way.
Yeah.
All right. So yeah, it's certainly pretty handy to choose a damping coefficient of like 1/64th rather than 0.01, for instance. Right. Okay, that works. Any other questions? So I thought I need to do just a little bit more on second order systems, then want to talk a little bit about time scaling, and then go back and look at the lab some more. In particular, some of the simulation stuff, and then go through a whole connection diagram, which apparently some people don't need. So oh yes, and by the way, tomorrow, February 14th, which is the 71st anniversary of the announcement of ENIAC, which is arguably more important than it being Valentine's Day. But that's just a piece of trivia. So we started out with, on the second order system, a spring mass system, which you probably all remember let's put the mass down here as minus k over m x minus d over m dx dt. And we've got to go through a couple of steps to convert this into the hardware format. The first is to factor the equation, and then the next is to convert that to a block diagram. And I put that in here someplace if only I could find it. Yeah, and we're going to notice that if we give some variable v1 is equal to x, then v1 by dt is equal to x dot. We're going to call that v2. So those are going to be our state variables, and we're going to integrate each one of those according to a scheme where, and you would have thought I could have, there we go. So we're going to say that v2 multiplied by dt. Now remember, you're going to pick dt carefully to be a factor of 2, so that this multiply is actually just a shift right. And then we're going to add this against a register, but we're going to mux it so that we can choose an initial condition or the output of the adder, so that V2 new will be here after every time step. And we need a clock here, clock input, to step the solution forward. And then V1, I'm sorry, this is V2. This is V1 new, because V1 is the integral of V2. And then to calculate V1, we need to integrate the second derivative. So we're going to form the second derivative as V1 times minus K over M plus V2 times minus D over M multiply by dt, of course, and then add with a mux and an integrator, a register, fed back to the adder to form V2 behind the board here. We'll call this V2 out here, V2 new. So the transformation is going to be from differential equation to a hardware form. And one thing that we haven't talked about then is how do you actually get that, how do you pick dt? Because we're using an Euler integrator, which is a very low order, it's as low order an integrator as you can build, the accuracy is not very good. So you have to take small time steps, because what you're really doing is you're simulating the function as if it is the value at the first part of at the first edge of the step, and not say some average value along the step, which suggests a higher order method for calculating this. If you take the average of 2 and use that instead of the leading edge, what's it called? Anybody remember Simpson's rule? Anyway, it's called Simpson's rule. So, but we're going to use a first order step. I did a couple of experiments to see how fine the step had to be. And it looks like 2 to the -8th or 2 to the -9th is a good value. But what I wanted to do was to try and motivate, if you set this up, if you set up the second order system with the appropriate initial conditions and let it run, and then took the output and put it into the audio codec, you'd get some sine wave frequency. The question is, what real frequency would you get? Because I'm going to ask you, when you build this, to set the frequency to about 500 hertz. So we want to go from this abstract form where we're just messing with symbols into a real sine wave frequency. And to do that, we need to notice, let's say we pick something easy like a dt of 0.02, 1/50th. That's not small enough, but we're going to do that right now. And let's say that our clock, our update clock, is 50 megahertz. You're choosing both of these. If you choose both of those, that says that the unit time must be 50 times longer than this value. If you're updating at 50 megahertz, that means that the unit of time in real seconds is 1 microsecond. 50 steps at 50 megahertz. So the real time unit is 1 microsecond. Now, in the math, the natural frequency of a sine wave oscillator is set by the square root of k over m. So if we set that to 1, we say then that we're going to get 1 radian per 1 microsecond. Because a k over m of 1 means 1 radian per time unit. So that says that for this choice of dt and clock frequency, and mathematically that stiffness of spring, k over m equal 1, that we would expect to get a sine wave with a period of about 6.28 microseconds, or about 2 pi times the time step. So there are 3 ways of scaling the frequency. One is change k over m. Another is change the update rate. A third is change dt, but there's going to be a fairly narrow range where for dt in this particular simulation because of the low accuracy of the Euler integrator. Too big a dt, and you're going to deviate. You're going to deviate from a sine wave. In fact, what will happen first is that the natural frequency will start to drift. Too small a dt, you say, well, all right, we'll just set it to 2 to the minus 16. Uh-oh. You do that, you shift all of your values by 16, you got no places left, everything is always 0, and the system fails. So you're sandwiched fairly narrowly between about 2 to the minus 8 and about 2 to the minus 10 or 12 or so. And that's all you've got. So you can't really mess with dt very much. And I'm going to suggest that for reasons we'll see in a minute, of about 2 to the minus 9 for dt. So really what you have left is you could change k over m. You can't go too big a dynamic range in k over m for the same reason. You're multiplying a variable by that, and if you make it too small, you're going to start losing significant digits too much. And you can't make it bigger than 1 because we can't represent any number bigger than 1. However, you can change the clock rate arbitrarily without changing the accuracy. So, in fact, in general, unit time is given by 1 over f clock times 1 over dt. So you pick a dt, you pick a unit time. I want it to be a kilohertz. I want a kilohertz output or so. Well, that would say that's about 6.28 times 10 to the third radians per second. So that's something like 160 microseconds, right? So with that, we can now get f clock. We're going to take the 50 megahertz, put it through some sort of divider, clock divider, to get down into the audio range or to get to whatever frequency we want. So I tried I tried a couple of experiments. One was I set dt equal to 2 to the minus 8. Any questions on this? Yeah.
This might be a bit of a silly question, but so with the hardware compiler for Verilog, if we put dt to be a multiple or a power of 2, will it know to make the multiplier a shifter?
So now you're asking how smart is the compiler?
Yeah.
And there are times at which Quartus 2 is remarkably smart. For instance, in some cases, if you multiply by any constant, it doesn't make a hardware multiplier. It just instantiates a bunch of adders. I would use a shifter to make sure that it's not instantiating a multiplier. Any other questions? So you can scale time the way you want. And oh, by the way, in old-style analog computers, you had to do that also by changing the integration time constant, which is really equivalent. But I tried, with a second-order system, I tried setting dt equal 2 to the minus 8 and calculating f out, the sine wave out, through the appropriate scalar, through the appropriate clock rate. I think I did 50 million divided by 64. I calculated f out should be 485 hertz, and I measured it at 476 hertz. So the natural frequency, the eigenvalue of the system, had shifted a little bit. How much? About 10 out of 400, so that's about 2.5%. If we go to, if we went to 2 to the minus 9, 2 to the minus 9, but the frequency I measured was 485. Now, the accuracy of the oscilloscope is about 3 places. So this might have been fortuitous, but it's probably good enough for what you're doing in this lab. Any questions? So let's go back now and talk a little bit about the process. As I said last time, you start by simulating in MATLAB until you find out what the system can do. How many people have done that? You guys have. That's easy. Since the code is written for you here, there's a reference. Oh, I won't do that. The next step then is to convert the constants in MATLAB, the floating constants, into fixed point, unless you pick factors of 2, in which you can do it by hand. And then to simulate in Modelsim. Now, what I am simulating in this example is just a direct digital synthesis unit, which is kind of an integrator. It's integrating phase, which happens to be a linear function, so it's really easy to integrate. You just add. So at the positive edge of the clock, if we're reset, we set the accumulator to 0. Otherwise, we increment the accumulator by some frequency-dependent increment, where the increment actually sets the frequency of the synthesis. And There's one other module, which is a lookup table that converts the phase accumulator into a sine wave. And what we want to do is, rather than synthesize that, is to simulate it. To do that, we have to put a wrapper around this that simulates all of the signals coming in to the module, so that the top level module, the test bench, so to speak, is a simulation module, which means that you have to use simulation syntax. You have to define a time scale, because now we're just doing it in software and time means nothing to software. And we're going to specify various signals as usual, but then we have to explicitly initialize them. We have to give them a value at t equals 0. Because again, time means nothing in a formal sense here. And we're going to start clock 50 at 0, clock 25 at 0, some index at 0. And then we're going to have to explicitly build a clock. And the way you explicitly build a clock in the test bench is to wait a few ticks. This means wait 10 ticks. What's a tick? A nanosecond, because that was the time scale we chose. We wait 10 ticks, 10 nanoseconds, and invert the clock. So every 20 nanoseconds it repeats, and that's 50 megahertz. Then we're going to do the same thing for clock 25, but wait 20 nanoseconds. Then we have to initialize reset carefully. And quite often, very often, you'll get undefined outputs from a workbench simulation. And an undefined output is almost always the result of an improperly constructed input signal, usually reset. So what you're going to do here, again, is you're going to reset. You're going to drive reset low at the beginning of the simulation. Then you're going to bring it high to force the reset for 20 nanoseconds, and then bring it low again, 30 nanoseconds, and then bring it low again. So this is going to simulate somebody with a very fast fingertip pushing the reset button. The index, why was I doing index? I was incrementing the index just so I had a register which was proportional to time, so I could count up nanoseconds by using one of the variables. Then we hook up the device under test. So it's the DDS unit device under test. And we hook up the clock and the reset, and we give it an increment, a phase, and an output, which goes to test bench out. And we have the direct digital synth that I just put up on the board. And then a sine wave ROM module, which is a really boring 256 lines of 16-bit hexadecimal table. You run this thing, and the first 4 times through you get undefined variables. But sooner or later you'll get to the point where there's some directions here that you should follow. Directions here you should follow. But in the end, what you're going to want to see is first a sine wave if you build a second order system, and then a pair of coupled sine waves when you build the fourth order system, when you build the coupled second order systems that are oscillating together. And you should be able to exactly match the sine wave, the MATLAB simulation if you choose the same constants. Once you do that, then you can be pretty sure that your calculation module is correct and that it'll compile and give you a valid answer and all that sort of thing. Then it's time to put your design onto the FPGA. I tried to be fairly explicit here in the assignment piece of this. Scale amplitude, scale time. You can set the mass to 1 so you can avoid the divide. You always want to avoid divides if you possibly can. Monitor VGA output, X1 and X2. You will notice down here that you want to take video screenshots and email them to the TAs because they love giant emails. And you can optionally suggest, you can optionally tell us that you'd like your video on the website and we'll put it up. But in the course of the demo, you'll be expected to arbitrary initial conditions for all three spring constants. Although in the interest of time, we'll probably go for some symmetry. We're going to ask you to turn on and off the cubic factor, the nonlinear spring. Did you get this nonlinear spring working too?
We didn't test it, but it should.
Code that's not written.
Yeah.
Code that's not written can do anything. Yeah. And particularly, it would be nice to see symmetric and anti-symmetric modes for testing. So I thought I'd draw out the wiring diagram for this. And this now is going to be the implementation of these two equations, the two second-order coupled differential equations, with the addition that the spring force 1 will have a cubic term instead of just that simple displacement term up there. So we're gonna have 4 integrators. Whose output is going to be x dot 1, x dot 2, x1, x2, and whose input is going to be determined by the sum of a bunch of different terms. In particular, minus d over m times, so we're going to make a multiply just look like a scale block, minus d over m times the velocity, minus k over m times the position, the nonlinear term x cubed here, taking the output and cubing it. The nice thing about fractional numbers is you can guarantee the cube does not overflow. Times minus k13 over m. And we'll just represent this input as having a switch on it, which can be on or off. But when you implement it, you might just change the value of k13 to 0. We also have to form x2 minus x1 multiply this output by k mid, the spring in the middle, over mass, and feed that back. And minus k mid over m fed back here. There'll be no cubic term on this on the bottom spring, but there will be a feedback for minus d over m here. Oh, this is K1. Then we have to have minus K2 over M here. And is that everything? That's just a spurious random mark there. I think that's everything. So each one of these is going to convert into an instantiated module. Yes?
Is the minus d over m for x supposed to be x2 or x2?
Thank you. You're quite right. So the subtractions you can just do in line, of course. The sums you can do in line. The multiplies are all by constants, except for this one where you have to take the product of the the variable with itself twice. And so you have a fairly good list of modules, so you need to come up with a naming convention for the signals coming out of them that makes sense to you. This is what you're going to put together and then test in Modelsim. You need 4 initial conditions, at least one of which has to be non-zero if you expect anything to happen. Otherwise, it'll just sit there quietly. Actually, that's not quite true.
If you set all the initial conditions to 0, you can still see it.
Why would that be?
Because like the spring that compressed.
Exactly right. So if if the spring constants are all equal and they're all 0, you should get no motion. But if the spring constants are not the same and you set them all to 0, then there'll be some stored energy in one of the springs. Did you have a comment on that?
No. Explain it to me. No.
Okay. So try some combinations in Modelsim, but to the degree to which you match the constants, you should get exact duplication with the MATLAB results, the Euler integrated MATLAB results, because all the math is exactly the same. Once that's done, again, then you start putting this onto the go from 1 piece of chalk to 3 pieces. So once this is all working in simulation, then you're going to want to bring this and this out to the VGA as a plot. And you can imagine various ways of doing this. Let's say that so the specs say that scale display, blah, blah, blah. Horizontal VGA should be a small multiple of the time step so as to show a few cycles. So it should look something like this. You don't want 100 cycles, you don't want 1 cycle, you want 5 cycles, 10 cycles. It's supposed to stop when you stop the simulation. It's supposed to erase when you start the simulation. What should it do after you fill one screen? Presumably it's going to continue going back to the start and redrawing over it, or it's going to scroll this way. That's actually annoying to do. So I would be happy if after you draw the 2 traces, that you start back over here and draw some more, and then you start back here and draw some more. Then you have to say, what should you do at the point where you're redrawing? What does the oscilloscope do in that mode? It actually erases a little vertical bar all the way across the screen. So when you're rewriting this point, the 10 pixels or so in front are erased, and then the old waveform is over here. And so what you could do is write a thin black rectangle on the screen just ahead of the point you're plotting. Maybe only 1 line wide, but probably 2 or 3 lines wide. This has a big advantage in that you don't have to remember the value for the whole waveform. You just erase everything along that. And it looks kind of like an oscilloscope display too. And all that should be done by the bus master rather than the HPS, right? That's going to be done by the bus master that you write, that takes the output and masters it into the VGA memory. Any questions on this? Yeah.
So, in your Modelsim, you had that index where you were keeping track of the time steps. Are you using that to verify your results at certain time steps with the MATLAB model, or?
You could. It gives a nanosecond tick.
Okay.
So you can compare nanosecond by nanosecond. That's probably overkill.
Okay.
But because the clock is running 20 times slower than that, and you're certainly not going to get any new information out of MATLAB in less than 1 tick. So that was that was mostly so when I was scrolling back and forth through the waveform, I could tell where in time I was in the simulator. I wouldn't bother to put that in hardware.
Okay.
You'll notice I'm not asking for a lot of annotation on this. I am not asking for horizontal and vertical time ticks and amplitude ticks, although you might do that. I'm not asking for that kind of level of documentation. I want to see just the two waveforms evolving. And with enough resolution that you can tell what's going on. I would say that even though the Nyquist criterion says you only need 2 points per cycle to understand a sine wave, the psychological criterion is that you need about 20 points per cycle to understand a waveform, a sine wave. You say, all right, well, we got 640, 20 points, 640 divided by 20. Sounds like about 32 cycles across the screen. That's the maximum you want to have. What else? I was telling a couple of people before class, I've been playing around with the video input modules. As of Friday, I had them working, except the video input was duplicated side by side. I had an idea of what might be wrong. I changed it this morning, recompiled, and now nothing works. Yay, Quartus! So I messed up something else, and I'll figure it out sooner or later. So you make a hypothesis, you change the code, you press compile, then you go read email for a while. Work on labs, come back 9 minutes later, try it. Doesn't work. Change the hypothesis, recompile, go off, do something else. That's what you'll do all semester. Anything else? So lab 2, what do you want to hear about next? What would be useful for lab 2? What do you want to hear more of for this lab?
It's more about the busmaster stuff.
Want to go back and go through the busmaster stuff again a little bit? That's a week or two old, so it's a little dusty. Sure, I can do that. Yeah, okay. Anything else? Let's spend a minute talking about final projects. Any ideas? I saw a good one today. There's a paper on how to optimally implement a neural net in an FPGA. That could be fun. Using all kinds of tricks to avoid multipliers and table lookups and all that kind of stuff. That could be fun. Vision, all kinds of vision stuff is interesting. Gesture-controlled games, facial recognition, mood detection. Hard. That's hard. Sound processing. Sound synthesis. What else? OpenCL. Some of you want to go in the direction of a higher level C-type construct for the FPGA. I can talk a little about that. I can tell you everything I know in 10 minutes. I'll try and learn some more. Okay. Let's come back next time and talk about bus masters some more.